Dear learners, welcome to this web-enabled academic support from School of Sciences, IGNOU. I'm Dr. Sanjeev Kumar, Professor in Physical Chemistry. I'm going to take up a series of lectures on ionic equilibrium. In this first part today, the session is planned as follows. That is, to begin with, I'll talk about what are electrolytes and non-electrolytes. And in the context of electrolytes, we will see what we mean by strong electrolytes and what are weak electrolytes. Thereafter, in the context of weak electrolytes, we will talk about what do we understand by degree of ionization. Then we will take up different factors which affect the degree of ionization of weak electrolytes. Having done that, we will move on to defining what is meant by ionization constant, which basically is a kind of a quantification of the degree of ionization. It's a kind of manifestation of that. And then thereafter, we will talk about Ostwald's dilution law. And towards the end, we will sum up what we do in today's session. Okay, let's make a beginning. Let's make a beginning. What do we see in this picture? That means someone is trying to use wet hands, soapy hands, to play with the electrical things over there, switches and extension wire and all. We know that we all are advised not to operate electrical equipment with wet hands, or when we are standing in water or on water, we are advised not to kind of use electrical appliances. Do you know why so? It is so because commonly used water, whether it's water from tap or from pond or anywhere, or maybe rainy water also, so all that is conducting in nature. And because of this conducting nature of water, the electrical current may flow from the electrical appliance, be it any appliance for that matter, and that can flow into the human body and cause what is called as a electrocution or electric shock. That means the person who's using wet hands and dealing with some kind of electrical appliance has a chance of getting electrical shock over there. And question comes up is, what makes water conducting? Because if you really ask me, the pure water is electrically non-conducting. If you take pure means you take a distilled water, extensively distilled water, so that water has got very few ions, and it is, for all practical purposes, it is non-conducting. But it is the impurities which are dissolved in water, and that makes it conducting. The tap water what we use at home, that has a lot of ions in that is conducting. Rainwater is also full of lot of ions over there, that also is conducting. So any water from pond, as I mentioned earlier also, so they all are conducting in nature. Okay, now let's try to understand how do we ascertain whether some kind of sample of water is conducting or not. Let's take two different situations there. One, I've taken salt in water. There's an aqueous solution of salt, say sodium chloride in water, and in one case I've taken sugar in water, and in both the cases I've put some kind of a device to measure the electrical conductivity. That means just to see whether the system is conducting or not. So essentially what we have is there are two electrodes there. So one of them is through a battery and a bulb. So the electrode comes, the connections are coming like this. Now what we find is that in case of salt in water, the bulb is glowing over here. Whereas in case of sugar in water, bulb doesn't glow. What does it mean? This conveys that this aqueous solution of salt in water is conducting in nature, whereas that of sugar in water is non-conducting. And such solutions, that means the substances like sodium chloride or any salt for the matter, whose aqueous solutions are conducting are called as electrolytes. That means salt is an electrolyte. Whereas the solutes whose aqueous solutions do not conduct electricity are called as non-electrolytes. Sugar is an example of a non-electrolyte. Okay, so far so fine. Let's move ahead. And the explanation for this, that means why is it that water, the aqueous solution of sodium chloride is conducting? That explanation was given by Arrhenius way back in terms of what is called as a Ionic theory of solutions. What Arrhenius proposed was that is certain substances, when dissolved in water, they produce freely moving ions. I mean, it is a production of ions, and these are the ions which cause the conducting nature of the aqueous solutions there. And in this, the example we have taken here, we see the water molecules. We know the structure of water molecule. It is polar. There are two OH, the oxygen attached to two hydrogens, and both OH bonds are polar. And the molecule also is kind of a molecule as a whole is electrically neutral. Molecule is polar but electrically neutral molecule. So when these molecules move, there is no current carried by them. Similarly, the sugar, if you take a crystal of sugar dissolved in water, that separates into a large plenty of molecules of sugar, and each sugar molecule is neutral. So here again, there is no conduction as such possible there. On the other hand, in case of salt, sodium chloride, that generates sodium ions and chloride ions. It are these ions which makes the solution of sodium chloride conducting in nature. Okay. Now, to understand what kind of electrolytes are strong or weak, we raise a question here. Okay, let's not raise a question at this moment. Let's try to take two different electrolytes. So I've taken salt in water here, and I've taken acetic acid in water. And again, I do the same mechanism there. I try to see whether they are conducting or not. And we find that both of them happen to be conducting. In case of salt in water solution, we find that bulb glows fairly well. Whereas in this case, there is a dim glow over there. That means there's a bright glow in case of sodium chloride in water, and there's a dim glow in case of weak electrolyte like acetic acid in water. Okay. Now, what happens? Let's understand this here. This is very, very important here. Now, in case of sodium chloride in water, what basically is happening is the sodium chloride, the aqueous solution of that dissociates to give me sodium ions and chloride ions. And this particularly dissociates completely. That means there are a lot of ions which are formed there. That makes it strongly conducting there. It's a strong electrolyte. On the other hand, in case of acetic acid, what do we find is the acetic acid breaks down to give you acetate ions and hydrogen ions there. But this is not complete breaking down. And this process is called as ionization. That means here, this phenomenon, that means the generation of sodium ion and chloride ions from sodium chloride is called as dissociation. Whereas the generation of acetate and hydrogen ions from acetic acid is called as ionization. Now these two are very interesting and important phenomenon. You will find that in the books, normally these two terms, dissociation and ionization, are used interchangeably, but there is a very subtle difference between the two. Let's understand the two, this difference between the two here. We find that in case of dissociation, that is the example I've taken is of sodium chloride. Now the ions, the sodium ions and chloride, we know the structure of sodium chloride crystal there. We know that contains sodium ions surrounded by chloride ions, and each chloride ion is surrounded by a lot of sodium ions over there. We know the structure of that. Now, when you put that into water, the water molecules solvate these ions, and the ions separate out. That means the ions which are present in the system, present in the crystal, they are dissociated. They dissociate from each other and are released in the solution. Whereas in case of ionization, what basically is happening is the molecular electrolyte, say in this case we have taken acetic acid. Acetic acid is molecular electrolyte there. There's no ions in that. But this molecule somehow ionizes, breaks down to generate ions. So since it is generating ions, we say it is ionization. So here it is dissociation. So difference lies here. In case of dissociation, ions are already there in the system. They just dissociate from each other. On the other hand, in case of ionization, ions are generated over there. So that is a very, very important difference between the two terms, dissociation and ionization, which we interchangeably use it. But we should be very clear about that what is the difference between dissociation and ionization. Okay, I'm sure that you have understood the difference between the two terms there. Let's move ahead. Let's move ahead and take one more set of examples of strong electrolyte and a weak electrolyte there. So we've taken an example of magnesium chloride here, and we've taken that of water, ammonia and water there. Here what you find is there is a strong glow, it's a strong electrolyte, MgCl2 is a strong electrolyte, whereas solution of ammonia and water is conducting, but it's a weak electrolyte over there. Again, we can write similar equations there. So in case of magnesium chloride, there is a dissociation to giving magnesium ions and chloride ions, whereas ammonia generates, ionizes to give us ammonium ions and hydroxide ions over there. Okay, so from these two examples of acetic acid and sodium chloride, and now magnesium chloride and ammonia and water, what do we conclude? We conclude that generally the molecular compounds are non-electrolytes. For example, sugar. Sugar is a non-electrolyte. Or they can be weak electrolytes. For example, we take an acetic acid or ammonia even. Even that also is a weak electrolyte there. On the other hand, the ionic compounds, say sodium chloride or magnesium chloride, they are strong electrolytes. So that is very, very important there. So when we talk about strong and weak electrolyte, essentially what we are referring to is that all ionic compounds typically are strong electrolytes. Whereas the molecular compounds, they could be either non-electrolytes, that means they don't, their solutions do not conduct electricity at all, or they may be weakly conducting over there. Okay, now there is one exception here. The exception happens to be, say, HCl gas. HCl is a covalent molecule. But if you put it into water, after solvation, what we get is, we get HCl, that's a solution of it, that is basically hydrochloric acid. So that actually ionizes completely. We know that HCl is a strong acid. It ionizes or dissociates completely in a way, because it's not a dissociation in that sense of it, because we have just defined dissociation to be that ions are there which break down. They dissociate from each other. But herein, we should call it as an ionization. That means HCl, after solvation, ionizes, but it ionizes completely. Okay, it ionizes to the 100% extent. So it is a strong electrolyte, and this is actually an exception there, because it's a molecular compound but happens to be highly conducting. It's a strong electrolyte. Okay, let's move ahead and raise one more question here. Now suppose I've got two weak electrolytes. Will they have same electrical conductivity? How do we answer that? Again, we take an example here. We take two solutions, one of chloroacetic acid in water, one of acetic acid in water. Now, what do we find? Again, we do the same thing as we have been doing all these times. That means we are trying to set up the kind of mechanism to see whether they are conducting or not. If conducting, to what extent. What you find is that chloroacetic acid, this bulb is glowing much more than that in case of acetic acid. And what is found is that the chloroacetic acid is much more conducting than that of acetic acid. And we will see later on that if we actually make the calculation for the systems here, we find for equal concentrations, say 0.1 molar of this and 0.1 molar of this, chloroacetic acid will be about 8.8 times more conducting. That means there are 8.8 times more ions over there, because more ions means more conduction. Okay, let's go ahead, and just to quantify this thing, we define what is called as a degree of ionization. Because if you remember that, we just said in case of chloroacetic acid, there are more ions there, whereas acetic acid gives you lesser ions. So how do we quantify that? That quantification is done in terms of a parameter called as degree of ionization. And how do we define that? It is defined as, basically, it's the extent of ionization. That means to what extent does the weak electrolyte ionize. That is called as degree of dissociation or ionization. Both are here used interchangeably, because I'm using dissociation here because that is the way it was defined initially. Nowadays, it's better to call it as degree of ionization, alpha. And that is defined as the number of molecules of electrolytes which are ionized divided by the total number of molecules of electrolyte that are dissolved. What does it mean? Now suppose I have made a solution and I have taken, say, 1 million of acetic acid molecule into water. Okay, they are dissolved. After that 1 million, maybe 1,300 get dissociated to give me as many ions over there. So 1,300 divided by 1 million, that is 10 lakh. So that will give me the degree of ionization of acetic acid, if I'm taking that as an example over there. There is another way of quantifying this that is actually also called as percentage ionization. Percentage ionization will be the number of molecules of electrolyte ionized divided by, this is basically same as ionization. But if you want to express in terms of percentage, you multiply by 100 because this is a fraction. Say it is 0.013. If it is 0.013, if I multiply by 100, that becomes 1.3. That means the extent of ionization happens to be, say, 1.3%. Okay, so this degree of ionization essentially is a measure of to what extent does the electrolyte ionize. Again, that's typically we use it interchangeably, dissociation and ionization, but we should refrain from using dissociation in this context here because it is more of ionization, because we know why we call it as ionization here. So it's a degree of ionization is the extent of ionization of a weak electrolyte. Okay, now let's move ahead. Let's move ahead and see that what are the factors which affect the ionization of weak electrolytes. Because if you take a strong electrolyte, typically by definition, a strong electrolyte is 100% ionized. That means it is completely ionized. So it is 100%. So the degree of ionization is more pertinent or more relevant in the context of weak electrolytes. And there are certain factors which affect it. Let's understand them. The first factor happens to be the nature of solvent. Any solvent which has got a higher dielectric constant is better. Now, suppose I take the solution of, again, take the example of acetic acid. If I take acetic acid in water, water is the solvent with the highest value of electrical constant. It's a very good solvent. So, the extent of ionization of acetic acid will be much more over there. But if I take acetic acid in some other solvent there, and some non-aqueous solvent, it won't ionize to the same extent over there. So the nature of solvent affects in that particular sense. That means any solvent which has got a higher dielectric constant will there will be a better ionization of the electrolyte in that. That's one. The second factor happens to be temperature. Typically, higher the temperature, more is ionization. It's like equilibrium. So when your temperature increases, there's more kind of ionization, or in generally, if you contrast, it's a dissociation there. So in the case of weak electrolyte, we're talking about ionization there. So higher the temperature, there is more ionization. There are more ions. There's more conducting. The third factor happens to be presence of common ions. And common ions, I'm sure that you learned about equilibrium in your school. And we know about the Leclerc principle. According to that, so the effect of common ions on the kind of extent of ionization of a weak electrolyte can be rationalized in terms of Leclerc principle. Suppose there is a weak electrolyte that ionizes to give you ions over there. And if you put a common ion, say, let's take the example of acetic acid itself. If you take acetic acid, that will ionize to give you hydrogen ions and acetate ions. And if I do this, if I add some sodium acetate will provide a common ion, acetate ions. So as a consequence, the equilibrium will shift into the backward direction. There will be lesser ionization. That means the extent of ionization of acetic acid has certain value. But if you add sodium acetate to that, the extent of ionization will decrease. That is what exactly is done in case of making buffer solutions. We'll talk more about it as we move ahead. Okay, the next factor we have is dilution. Typically, the extent of ionization of a weak electrolyte increases with dilution. If there is more and more of dilution we do, there is more and more of ionization there. And this, in fact, actually is expressed in terms of what's called as a Ostwald's law, which we're going to just take up now. Now, prior to that, I think before we come to Ostwald's law, let's talk about ionization constant. It's important because that is what we're going to use there. So ionization constant basically provides a quantitative description of extent of ionization. What does it mean? We have just said that's one way of doing it, but that is the way we quantify a given the ionization in case of a weak electrolyte there. Let's take an example of a weak electrolyte, say AB, that ionizes to give you A plus ions and B minus ions over there. Now, for such a system, we know from your earlier studies of equilibrium constant, chemical equilibrium, we know that the equilibrium constant for such a situation, because mind you, in case of weak electrolytes, there is always an equilibrium between the electrolyte and the ions which are produced from there. And since it's an equilibrium reaction, we can write the equilibrium constant, and that happens to be, for this particular case, will be A plus into B minus by AB. These are the square brackets represent the concentrations there. Okay, if this is the equilibrium constant, then so we say that this equilibrium constant essentially characterizes the ionization, or if you, in older nomenclature, the dissociation. That's why this equilibrium constant is also called as ionization constant or dissociation constant, because in the books both the terms are used still. So I am using these terms interchangeably, but I have made it very clear to you that what does dissociation mean, and also what is the meaning of ionization. And also we know that in the context of weak electrolytes, it is the ionization which is a more appropriate term rather than dissociation. Okay, now so suppose that there is a greater the extent of ionization, higher will be the magnitude of ionization constant, or the reverse of it. If the ionization constant value is large, that means there is more ionization. Or if there is more ionization, the value of ionization constant will be more. Okay, let's go ahead and now look at what is Ostwald's dilution law. Basically, what Ostwald did way back in 1888, that is, he used he kind of applied the law of mass action to the ionization of weak acids. And what he observed, basically what he did was, by using the law of mass action onto equilibrium obtained as a consequence of ionization of weak electrolytes, and he formulated a relationship between the degree of dissociation, because that's what he used there. Though we're talking about ionization now, but that is a term he used there. Call it as degree of dissociation, and that is referred to as alpha, the concentration of the solution C, and the equilibrium constant K for the dissociation of weak acids there. And this is basically what led to the Ostwald's dilution law. Let's go further and see how do we work it out. We again take the same situation there, same equilibrium, electrolyte AB, ionization to give you A plus ions and B minus ions there. And if we have got a C mole per decimeter cube as the concentration of the electrolyte AB, and if we have assumed that the degree of ionization is alpha, I'm using ionization now, then what we can write is as follows. That is the initial concentration, because this is the equilibrium reaction I'm talking about. AB giving you A plus ions and B minus ions. Initial concentration is C, 0, 0. And now, if you assume that there is alpha is a percentage of ionization, alpha ionization, it's a degree of ionization there, then that will be changed due to ionization will be equal to C times alpha. It means if it is 1 molar, it will be alpha molar. If it was 0.01, it will be 0.01 into alpha. So alpha is extent. Okay, so this will be a change. That means the concentration of AB will decrease by this amount C into alpha. If that be so, then the concentration of A plus ions which will be generated will be C times alpha, because if there is one molecule of AB that dissociates to give you one A plus ion and one B minus ion, then C times alpha will give you same number of ions. So C alpha will give you C alpha of A plus ions and C alpha of B minus ions there. So once the equilibrium is established, what do we have? The final concentrations. The final concentration, it was initially C, it has decreased by minus C alpha. So the concentration will be, at equilibrium, the concentration will be C times 1 minus alpha. Whereas that of A plus will be equal to C alpha, and that of B minus will be equal to plus C alpha. Okay. Now, and we defined that equilibrium constant to be equal to A plus into B minus by AB. So what do we do now? In order to work out the expression for the equilibrium constant, we substitute the concentration of A plus, B minus and AB into this expression, and what do we get is the following. That means if you substitute the equilibrium concentrations, we find K to be equal to C times alpha into C times alpha divided by C times 1 minus alpha. That is the concentration of AB at equilibrium. If you just simplify it, the C crosses with this one, C cancels with this one, and what you get is C alpha square by 1 minus alpha. Okay, we go ahead and make a small assumption here, which is a fairly valid assumption, that if alpha is far less than 1, which typically is, as I just took the example of say acetic acid, so it ionizes to the extent of about 0.013 or maybe say 1.3%. So out of every 1000 molecules, only 13 are ionized. So to that extent, we can say that alpha is far less than 1. And if we ignore that, we can ignore alpha with reference to 1. Because alpha is very, very small as compared to 1. We can ignore this. We don't ignore it in the numerator. We ignore only in the case of denominator. And we can write K to be equal to C alpha square. Basically, K was equal to C alpha square by C 1 minus alpha. So if I just ignore alpha with respect to 1, so this term goes off, this becomes 1. So our K becomes equal to C alpha square. That's what we written here. Okay, if you just rearrange that, so from this, by rearranging, we can get the value of alpha to be equal to square root of K by C. And we also know that C is proportional to 1 by V. That is very understandable. Suppose I take certain amount of solute, put into water. If I take and say 1 gram of acetic acid, put into water, say 1 liter of water, there is certain concentration. If I add more water to that, it will become dilute. If I go on adding more and more volume, there will be more and more water to that. That means if I go on increasing the volume, then the concentration will go on decreasing. That means there is an inverse relationship between concentration and volume of solution. So we just substitute it over here. So for 1 by C, we can put it as V from here. There is a proportionality constant as well, definitely. So alpha comes out to be square root of K into V into some proportionality constant also will be there. If I take this square root of K out, so it becomes K prime. K prime is again a constant there. This K prime is constitutes of K, the square root of K, and also the proportionality constant what we had over here. So what we get is that alpha is equal to K prime by C, where K prime is essentially square root of K. Now, what does it mean? From this, we can work out our expression or the statement for Ostwald's dilution law there. What you found is this. That means alpha is equal to square root of Kb or K prime into square root of V or K prime by square root of C. So from this, we can say the degree of ionization of a weak electrolyte, that is alpha here, is directly proportional to the square root of dilution. This dilution of the volume there, or inversely proportional to the square root of the concentration that is over here. So this is basically Ostwald's dilution law. Now, in order to this, experimentally what we do is, this is the way we can write down, this is the expression, this is the kind of statement for Ostwald's dilution law, and this is a mathematical expression for the same. Now what you will see is, in order to know about these things, we need to have some means of measuring this alpha. And that is very simple. Experimentally, alpha is measured, is defined as alpha is equal to lambda V by lambda infinity, which I'm sure that we are familiar with these terms. You must have learned about these terms in the electrochemistry of your school, wherein this alpha V is the equivalent conductance at infinite dilution. That is, equivalent conductance of the solution at a dilution V. That means a certain amount of dilution there. At that dilution or that concentration, what is the value of equivalent conductance for the system? And this we divide by lambda infinity, which happens to be the equivalent conductance at infinite dilution. That means the system has become so dilute and there is no further ionization on adding more water to that or making it further dilute there. So this ratio gives you, because this basically is equivalent to when there is 100% ionization, this will give you equivalent conductance at a certain concentration there. So that is the way we have defined our alpha. We have defined alpha to be is a ratio of how many molecules are ionized to the total number of molecules in solution. So that we can work out by using these terms. We'll talk more about it when we talk at a later stage there. Okay, now let's sum up what we've done. What we've done is we basically started by defining what are electrolytes and non-electrolytes. We took some examples and tried to define that. Then we took another set of examples to differentiate or to clarify what do we understand by strong electrolytes and weak electrolytes. Thereafter, in the context of weak electrolytes, we defined a term called as degree of ionization, which basically is a measure of extent of ionization. Thereafter, we discussed 4 different factors that affect the degree of ionization, and thereafter we moved on to defining what we understand by ionization constant. Basically, it's a mathematical way of representing the extent of ionization there, or rather you can say representing the ionization equilibrium. That means the ionization of a weak electrolyte. So that equilibrium can be expressed in terms of, quantitatively can be expressed in terms of ionization constant. And then thereafter, toward the end, we talked about Ostwald's dilution law, which basically relates the degree of ionization to the extent of dilution of a given solution there. Okay, so with this we close here. In the next session, we will talk about what you say. We will try to review the different theories we have for acids and bases there. Thank you very much.